Hello everybody. Let's talk today for a few minutes about how you can determine the equation describing the relationship between variables from a graph. The first thing you need to do is plot a scatter point graph and find the best fit line for the data. Now we've already talked about how this is done in an earlier part of the lesson, and we usually use Logger Pro or some other graphing software to help us do this quickly and accurately. The second thing you need to do is determine the generic equation that describes that best fit line. Third, once you have the generic equation, you substitute the symbols for your actual independent and dependent variable in for the generic x and y in that generic equation, and this will give us an equation that we call our specific equation because it describes this specific relationship. Finally, we compare our specific equation with our known equations if they're available, and that'll help us figure out the significance of the numerical constants which are in that equation. So for this course, there are only 4 generic equations that you'll need to remember. Let's see what they are. To start with, here is a pair of graph axes. Remember that when using standard protocol, that horizontal one is called x and the vertical one is just called y. The first common relationship that we often see happens when increasing the x variable causes the y variable to increase at the same rate. That results in a best fit line that's just a straight line. And we call this a linear relationship, or we just say that the variables are directly proportional. The generic equation that produces that kind of shape is just y is equal to kx plus b. The second common relationship that we often see looks like this when you plot the scatter point. Here, as the independent variable gets bigger, the dependent variable gets smaller, and it results in this downward curve. This type of relationship is called an inverse relationship, or we just say that the variables are indirectly proportional. The generic equation for any inverse relationship is y is equal to k divided by x. The third common relationship we see is when the independent variable increases and the dependent variable also increases, just like in the linear relationship, but this time the dependent variable is increasing faster than the x variable. That results in a scatter point with a shape that looks like this. The generic equation that produces this shape is y is equal to kx squared. And the name of this, we usually just call this a power relationship, or sometimes we just say that the variables are exponentially related. The last common relationship is similar. In fact, it's also a power relationship, but this time the dependent variable is proportional to the square root of the independent variable. And it results in a curve shaped like this. The generic equation here is written as either y squared is equal to kx, or sometimes you'll see this one written as y is equal to kx to the 1/2 power, because squaring the y variable or square rooting the x variable mathematically are equivalent to each other. So, these are the 4 common relationships that we typically find. These will be the 4 generic equations that you will need to remember. Now, let's look at how we can apply those to figure out a specific equation. So here's an example of a displacement versus time graph that was made from that graphing assignment earlier in the course. Notice that the data points all fall essentially in a straight line. So we look at our scatter point, and we're going to use Logger Pro to put on the best fit line. We say, well, that's a linear relationship. We tell Logger Pro to put on a linear best fit line. So here's that same graph after having the best fit line calculated and put on. Notice that Logger Pro gives you the equation for this best fit line right here. You're also given the values for the y-intercept and the correlation and the root mean square error statistics as well. Now, recall that the generic equation for any straight line is y is equal to kx plus b. Let's see how these compare. The independent variable on the x-axis is time, or just t. Since t corresponds with this x right here, we can see that that is why it was put into the equation in this spot up here. Also, the dependent variable is displacement, which we represent with a capital X. We can then just substitute that capital X for this y in our generic equation, and that's why it's located up here in the specific. Finally, we can put in the values for the slope of the line and the y-intercept, and we now have our completed equation, which is specific to this motion. Now let's see about the accepted equation. We already have the generic and specific equations. We're going to compare that to our known equations describing linear motion. These are the average velocity is equal to the change in displacement divided by time, acceleration is equal to final velocity minus original velocity divided by time, change in displacement for an accelerating object is equal to the original velocity times time plus 1/2 at squared, and final velocity squared is equal to original velocity squared plus 2ax. Notice that the equation that we're going to need has got to include an x for displacement, and it's got to have a t in it for time. Notice there's really only one equation of these accepted ones that does, and it's this one right here. If we take that equation and algebraically solve it for x, it becomes x is equal to average velocity multiplied by time. This then is our accepted equation. Also, notice that in this position right here, it corresponds with this value in our accepted equation. This lets us know that the average velocity of the object in this motion was 0.0240 meters per second. Okay, so that's how you determine the generic, specific, and accepted equations from graphs. I'll let you get busy graphing. Bye.